Now in this session, one of the main points is to show you with an actual demonstration that often the equivalent DFA of a given NFA is often a lot more complicated. Now, actually, previous session I think I said we would be talking about the equivalent DFA of N1, but actually it's N2. In other words, you're looking for the strings where the third last symbol is a 1. Okay, so I made an error the previous session. Okay, so we're trying to find the D. Well, you're given. In fact, here it is. You can see it's just a mess, right? So the point is that for this NFA N2, the NFA that pinged again, just a minute. So the NFA is N2, right? It's the one that is trying to recognize the language whose strings have the third last symbol being 1. All right? Okay, so here it is. Here's the the equivalent DFA, deterministic. You know, there's no repeats. You know, it's definitely a DFA if you look carefully at it. But I mean, look at it. Just your first impressions. It's a mess, right? For a start, it has like 8 states, whereas this from the previous session had 4. Okay, so it's more complex. You know, all these transitions, and you know, it's a mess. And I think this is the simplest equivalent DFA of this NFA, right? And it has double the number of states. Okay, and certainly this is much harder to understand than the NFA. So you beginning to appreciate the value of NFAs, because you know the equivalent DFA can be a lot more complicated. Here's a concrete example of that idea, right? Okay, so here now's a bit of homework for you. Give you, you know, get you working on NFAs, and when we come to the end of the chapter and start on the problem solving, there are, let me check again, I think there was 60-something questions. It was a huge problem-solving section. And quite a few solved solutions, which is helpful. Yeah, 65 questions in the question section at the end of the chapter, the end of chapter 1. So you'll get plenty of practice, you know, if you're getting into this seriously. All right. So here's a homework question. Give you a taste. Say now to your NFA. Obviously, you can't add eters to a DFA by definition. It's not allowed. It's not a DFA anymore if you add eters. But add eters to your N2 between the transition between Q2 and Q3, and the transition between Q3 and Q4. Okay, so you add these 2 eters, and the question then is, so you've now got your N2 is now modified, and the question is, what language does that modified N2 recognize? Okay, let's do that for homework. All right, and I put here good luck. So, so try now modifying the DFA. In other words, this one. That's the equivalent of this modified N2, right? Now the modified N2, will have 4 states. So in the previous session, you had the state diagram for N2, and you modify it just by adding two eters, one between the transition between Q2 and Q3, and the second eta you add to the transition between Q3 and Q4. So it's a minor change, but try to find the equivalent DFA for this modified N2, right? And I've just said good luck. Okay, you can do that for homework if you like challenges. All right. Okay, so now another example of an NFA. So example 1.33 in the text. Okay, so it's our third example. So we'll label this NFA N, N for non-deterministic, N3. The alphabet now is unary. It's not even binary, right? It's unary. We only have one symbol in the alphabet, right? Call it 0. So it's a unary alphabet, right? Just one member. And let's use the symbol just 0. I mean, it could be anything, but we'll just use 0. Okay. Now here you're given N3. This third example of a non-deterministic automaton, and it's pretty simple. You just look at this. Can you guess what its function is? Now, this state diagram illustrates how useful these eters can be. So, that's what it says here. It shows the convenience of using these eta arrows, these transition arrows. So, what's going on here? Well, this is your start state, of course. Here's your isolated arrow here. So this is your start state. Now, all these states are the same. They have to be. Is that right? Makes sense. Does that make sense? Because there's only one symbol. Now I'm confused. Because there's a difference between these two, right? That's an end state, an accept state, and this isn't. Now I am confused. Okay, they're separate states. These are input signals. Oh, it keeps pinging. I'm going to have to work on this problem. It's annoying. Okay, so distinction between states and input symbols. So we have how many different states? So they're not marked. It's confusing. So maybe 2 or 3. That's something to think about. This is how it appeared in the text, but they weren't marked. The states weren't marked. All right. Okay. So you come to your start state. Immediately you see you've got 2 eters. So you have whatever state that is. You could stay there. You generate a copy for this state, whatever it is. So you'd have 2 machines running here, but you've got this state also eta. So you have a third machine that whose state would be this. Okay. So you're here, here, and here in a sense. You have these 3 states in the next step. And so effectively is that right? 3 machines or 2? 3. This one I find more puzzling. Anyway, so at least you're here and here, and then all these zeros come in, but how many of them? Now, if when you've read the last input symbol, and let's say you're here, because all this looping, and you end up here. So if you have an even number of zeros in your string, you'll end up in that state. So when it stops reading, you're in an accept state. Right? Now, if you branch this way, if your string has a multiple of 3, has a length of a multiple of 3, you'll end up here. Okay. So in other words, this machine here, this NFA, its job is to detect whether the length of your input string is a multiple of 2 or a multiple of 3. Okay? And I have a bit of a question mark here, like it's an eta. Okay, so you should have like 3 machines. So I'm still a little confused about this. Okay, so this machine should accept any any string of length multiple of 2 or of length multiple of 3. So it would accept this, yeah, that's even, a multiple of 3, okay, that's even, okay, but it would not accept just one symbol, 0, because that's odd. It's not a multiple of 2 and it's not a multiple of 3. Now it would accept 3, but it won't accept 5, because 5 is not even and it's not a multiple of 3. Okay, so that would be rejected. Right? So you can think of this kind of machine as yeah, I think you do. Yeah, you do need this, because you could stay in that state many times, right? And then finally you think, oh, now's the time. Let me check to see if its length is multiple of 2, or go this way and see if its length is a multiple of 3. Okay. So when do you branch here or here? Well, you could stay in that state, I guess. I need to think about this a bit more. I mean, you too, and analyze this. You're given this state diagram. How does it work? I find it a bit confusing that Sipser did not put state identifiers in this diagram. All right, now you could make a machine for this task, for this language, without using the etas. Make things a bit more complicated. You could even note find an equivalent DFA for this task. Okay. But for the task, this N3, this one, using the etas, is the easiest for the task. So you're beginning now to get an impression of why these etas are useful, and hence NFAs are useful.